All right. So let's put away the quizzes. So yesterday, we got our crash course into conjugated pi systems, right? And we said that the simple trick for finding a conjugated system is you have alternating double single bonds. And it doesn't always have to be carbon-carbon single bonds. It could be carbon-oxygen double bonds or even carbon-nitrogen double bonds, just as long as you have that alternating framework. And we said, we said that the unique thing with these systems is that bond that I have highlighted in yellow actually has restricted rotation. So these don't rotate as freely as one would naturally expect, right? And that's due to the delocalization of electrons along that entire pi system. And we said we could draw this with a molecular orbital view where all of these p orbitals have to be aligned in order for resonance to occur. And because of that, we're actually providing a lot more rigidity to this molecule. So I want to show you a unique example. Yeah?
So when it is in the far right resonance structure, even though it's binary,
yep.
and the bond to the left of it's now a single bond, so that can potentially rotate then?
So the question was about this bond right here?
Yeah.
Yeah, so if we think about that, this isn't going to be as rigid as a normal alkene, right? Because it's not a true alkene, it's in between a single and a double bond. Yeah, so it's actually easier to spin than a normal double bond. In fact, this is how our vision works. We have conjugated molecules in the rods and cones of our eyes, and those double bonds, when they are excited with the correct energy of light, meaning a wavelength of light or a color of light, you can actually break that and they can spin around and trigger proteins. Those proteins will then tell your brain, hey, you're seeing a red color in this space. So it's pretty unique, I think. All right, so let's take a look at an example. We'll come back and talk about that a bit more later. All right, this example is one that we're going to see a lot of, so I really want to drive it home. What's the name of this molecule? It's a diene. We got to be more specific, though. So we go through and we can number it 1, 2, 3, 4. So it's a butane molecule, right? But it's got 2 alkenes in it. So we could go through and we could name this 1,3-butadiene. If you remember going back to last term in the video, I had an example with dienes in it, or trienes for that matter. Make sure you remember how to name these. In particular, though, this bond right here that I've highlighted in yellow is really similar to the bond we were looking at yesterday, right? Yep.
Does it not need to be called trans?
That's what we're going to talk about. Yeah. So that bond between carbon 2 and carbon 3 has restriction of rotation, right? Because it's conjugated. In this case, even though it's a single bond, we need to designate it as cis or trans. So in this case, in order to do that, we call this, whoa, that's not what I want. We call this S-trans 1,3-butadiene. And what the S stands for is a single bond that has some restriction to rotation. And in this specific conformation, it's trans, right? Meaning the 2 dienes are facing opposite directions. The cool thing with this, though, is with enough energy, you can actually spin that, though, right? So chemists have been able to measure the amount of energy input required to cause this bond to rotate freely in space, and it's about 15 kcals per mole. Way, way, way higher than a normal single bond, right? So this has a fairly sizable barrier to rotation, but we can push it to rotate. And when we do that, we can get this molecule that would be S-cis 1,3-butadiene. Which one is more stable? Trans, why? Yeah, if we think about this, right? This molecule is going to have some steric clash between those 2 groups. They wouldn't want to be near one another unless we're forcing them to be, right? So this one on the right is less stable. What does that tell you about the reactivity? Is it going to be more or less reactive? More reactive. Yep.
So if we were to reverse it, does it take just less energy to reverse it, or is it going to give off?
So if we reverse it, we'll still have a barrier to overcome because we still have partial double bond character, but it's going to be energetically a lot more downhill, meaning the delta G value is going to be negative rather than going this direction, which delta G would be positive. Does that make sense? So this is not going to be a spontaneous reaction. All right, so now let's take a look at what this looks like with, or actually, sorry, I'm going out of order. Let's take a look at how we prepared these. And this will be a little bit of review. So I want you to help me predict what reagent we would need to accomplish the formation of butadiene. What reagent would we need for this reaction? Looks like elimination, so we needed a base. Yeah, terbutoxide. Would this be E1 or E2? E2, because it's a strong base. So this is kind of review of first term chemistry. Or we can do this from a dihalide. And I'm not even going to be concerned about stereochemistry here. All right, what reagent would we need here? Terbutoxide in excess. Why are we going to avoid using something like sodium hydride? It would favor the Zaitsev product, and we want the Hofmann elimination product. So we do need to typically use a big bulky base to favor our Hofmann elimination product. And then the cool thing with this is we can actually make this from a non-conjugated molecule by just simply adding in elemental bromine. So we can go from a non-conjugated alkene to a conjugated diene by doing halogenation followed by subsequent elimination. Does that make sense? So just kind of review of a little bit of our addition and elimination chemistry. All right, so now we've got to take a step back into Gen Chem a little bit. How many of you remember molecular orbital theory from Gen Chem? In fact, I think they're covering that right now in Gen Chem, so I've had some of their students talk to me about it. It gets way crazier when you get into conjugated systems. So let's take a look at the conjugation picture for 1,3-butadiene. And what I want to do first is draw a simple MO picture. If we think about it, we've got 4 carbons. All of them are going to be sp2 hybridized. And in fact, I'm not even going to bother drawing in the hydrogens. They're not the interesting part. What is the interesting part is the p orbitals coming off, right? And we know in the system, in order for resonance to occur, we actually need all of these p orbitals to be aligned and in plane with one another, right? So this is kind of the simplified molecular orbital picture that we talked about kind of at the start of the year, explaining pi bonds versus sigma bonds. The reality gets a lot more complicated though, right? Because if we think about this p orbital, we'll just pick on one. One lobe is actually going to be a different phase than the other lobe. We've kind of neglected talking about phases of the p orbitals, right? So let's take a look at the molecular orbital picture. And in order to draw the molecular orbital picture for this, let's start out focusing on this picture on the right. So what we're taking is 4 separate p orbitals in all of our aligned carbons. One half of the p orbital is going to be opposite phase of the other half, right? And then what we do is we come up with these molecular orbitals. Molecular orbitals are different than atomic orbitals. Essentially, they're going to be the average orbitals of the entire molecule, not just one specific atom. And if we think about it, the lowest possible energy state is when all of these orbitals are aligned. And then we can go up one energy step. And in this next energy step, we're going to have a node where we actually have a phase change between adjacent p orbitals. So this is going to be called a node. And then once we go above that, we're going to create 2 nodes. And then above that, none of the p orbitals will be in phase. If we think about energetically, this is really unfavorable because we can't share electron density if the orbitals are out of phase with one another. That's actually destructive, not constructive interference of those waves. All right, and then if we think about the number of electrons in this pi system, we've got 4 electrons. So we can go through and kind of label them. And just like any ladder, we start from the bottom and we fill going up. So if we think about the orbitals, molecular orbitals that are occupied, really only these bottom 2 are. And the reactive one, in this case, is going to be this set of orbitals. In many ways, this is the best view of the overall molecule, right? It looks a lot more like what we had drawn up here. All right, so now what we need to do is talk about some of the terminology. So this orbital is occupied with electrons in its ground state. This is called the highest occupied molecular orbital. This is usually just abbreviated as HOMO. All right, and then up here, we've got an orbital right above it that is unoccupied. And what we call this is the lowest unoccupied molecular orbital. And this is called our LUMO. The crazy thing with this is we can really accurately measure the energetic difference between these 2 orbitals. Does anybody know how we do that? By exciting the electrons, right? We can see what frequency of light gets absorbed by this molecule. And from that frequency of light, we can extrapolate out the energy of those photons, right? And from that, we can deduce there must be this difference in energy between your highest occupied molecular orbital and your lowest unoccupied molecular orbital. This is called your Homo-Lumo Gap. It's really important with photochemistry in particular. Does that make sense? It's kind of crazy, but the weird thing you have to remember is the step system where you start out with 0 nodes, then you go to 1, 2, and 3. So really you take the number of conjugated atoms in that system and you can subtract out 1, and that would tell you you've got the possibility of 3 different nodes in your system. So 0, 1, 2, and 3. All right, let's look at a harder system. What happens if we continue this conjugation? All right, so the simple MO picture for this one has 2 additional carbons. We still have a bunch of p orbitals sticking up and down like this. And in our super simplified view, we would look at each of those bonds as being pi bonds, right? So this would be an example of a triene. But like we said before, one side of your p orbital is going to be out of phase with the other side. So again, if we go and we look at this, and this is all in your textbook, I know it's hard to copy down, but this time we're starting out with 6 p orbitals. The lowest energy one is where they're all going to be in phase with one another. Then we can go up, we can apply 1 node, we can have 2 sides that are out of phase, and then 2 nodes. This looks a heck of a lot like our simplified molecular orbital picture. Then we can go up and we can do 3 nodes, followed by 4 nodes, followed by 5 nodes. Just like before, we know we've got 6 pi electrons, so we can fill these up. So that means that this must be our HOMO, our highest occupied molecular orbital. This one up here would be our LUMO. And with enough energy, we can excite those electrons from the highest occupied molecular orbital up to that LUMO level. And like I said, we can measure this using photons, for example, if this gap is small enough. So photons have enough energy for a lot of these conjugated systems to excite one of those electrons up. So the cool thing with this is that the more conjugation that you have, the smaller this Homo-Lumo gap gets. It actually shrinks down in energy. So let's make a little note about that. So more conjugation equals smaller Homo-Lumo gap. And this is referred to as frontier molecular orbital theory. Frontier molecular orbital theory basically neglects all of the orbitals outside of your HOMO and your LUMO orbitals. Those are the ones that are most interesting because you can excite your HOMO electrons to your LUMO level. Yep.
If there's two similar molecules that they have the same amount of conjugation but like slightly different formulas, are the gaps going to be similar because of the conjugation, or are they going to be just very wild?
So the question was about the Homo-Lumo gaps for molecules that are similar. There's actually a whole set of rules called the Woodward-Fisher rules, I believe, where you can go in and predict. However, in modern day chemistry labs, you use computational systems to really help you predict. But the big takeaway from this is more conjugation, because it has a smaller LUMO gap, can be excited with lower energy light, meaning more red-shifted light, if that makes sense. So more conjugation indicates that the molecule is going to get red-shifted. So this impacts the colors of molecules a lot. A lot of the compounds that we've been looking at so far this year are colorless because they're not very conjugated. But when you get into highly, highly conjugated systems, for example, beta carotene, then they start to appear colorful to our eyes, at least. All right, so that's kind of our crash course into molecular orbital theory. If you want to go through and read the book in more detail, you're more than welcome to, but we kind of got to continue on to reactivity a bit. But this helps explain why there's some restriction to rotation. So if we go back up and we look at this one, this bond right in the center here, I'll highlight it. If we excite it with the appropriate frequency of light or energy, actually it behaves a lot like a double bond. So that at least is a theory that helps explain why that occurs. All right, the next one, I really like this reaction because it's something you can intuitively infer. So I'm going to give you a minute to work on this one. I want you to predict with your neighbor what will happen if you react 1,3-butadiene with HBr, and I'm going to specify there's only one equivalent of HBr. There is not two. So I'll give you a minute to work on this, but check with your neighbor. And I'll give you a hint. There's more than one possible product. So see if you can figure out the mechanism. All right, I'm going to get us started at least to our intermediate, not necessarily to our final product. So just like with any alkene, you can have your alkene act as a nucleophile and attack HBr, right? So this looks a heck of a lot like what we saw day one this term. All right, so now the question is, will the hydrogen end up where that green arrow is or where the orange arrow is? What do you think? So where will the hydrogen end up? Green? Why? So let's draw both out, right? So just like last term, you can draw out both possible options and then say, all right, which of these is more stable and therefore more likely? The one on the left or the right? Left. Why? So not only is it more substituted as a carbocation, but it has resonance, right? Resonance is even more powerful than substitution. So in this case, this is definitely going to be the correct choice. And in fact, I'm just going to leave that hydrogen on there for the time being. And let's consider the resonance structure for this. All right, so we can kick those electrons over. And we can delocalize that positive charge. Are there any others? I don't think so. So those are our two major resonance contributors for this conjugated system. And it's important to remember that we still have bromine or bromide floating around. So I'll let you think about what could happen with that bromide. So see if you can figure out why we're getting multiple products. All right, does anybody have an explanation for why we're getting more than one product? So that's a good question. So you were talking about rearrangement. When resonance structures are drawn, are they really rearranging? They're kind of in between, right?
Yeah.
So it's a hybrid of both of the structures we have drawn, which means that this carbon right here has partial positive character, and this carbon right here also has partial positive character. So if you're the bromine, doesn't matter, you could attack either one, right? So let's consider that. So if we've got bromide floating around, bromide could attack either one of these positions. It could attack in right there, or it could attack in right there. The unique thing with this bromine, it could attack from the top face or the bottom face of that p orbital, right? Yep. Yeah, and in both of these resonance structures, they're both resonance stabilized. So it's valid that the bromide ion could attack either one of those carbons. Absolutely. So let's take a look at the two different structures we would get for this one. We could get one where bromine is a dash or a wedge. I'm just going to simplify this and write plus En. And then over here, bromine attacked off the end. We don't have any stereocenters in this one, so it's nothing we need to be worried about, right? So these would account for our three different products. All right, when we look at this, one thing we can do is we can take a look at what was added in, right? So if we look at the molecule on the left, these were the two atoms that were added in. And we would call this 1,2 addition simply because if we number these carbons, they're 2 carbons away from one another, right? So it'd be 1,2 addition. If we look at the one on the left, we added in 2 different groups, but this time they're further away from one another. We go 1, 2, 3, 4. So this would be called 1,4 addition. It's unique to conjugated systems. If we think about a normal alkene can only ever do 1,2 addition because there's no resonance stabilized intermediate. 1,4 addition, however, can occur with conjugated molecules. Yep.
So if we're naming it like 1,2 addition or whatever, it doesn't matter how many, like the functional groups, whatever, like it's not attached to the 3 and 4 carbons, it's just how many weighted are. Yeah,
so the numbering is just counting how many carbons are in between the 2 new atoms that were added in. So in this case, it's 2 versus 4. All right, now my question is, which of these is more stable, the 1,2 addition product or the 1,4 addition product? So you think 1,4 is more stable than 1,2? Why? Close. The double bond is more substituted. If we look at the alkene over here, it's di-substituted versus over here, it's mono-substituted. So this is the more stable alkene. This is the less stable alkene. All right, if something is the more stable product, what would we refer to that as? So how many of you remember talking about kinetic versus thermodynamic products? Which one would the more stable product always be? So think about it this way. Kinetic talks about speed, not stability. Thermodynamic talks about stability, right? So this one on the right would be our thermodynamic product. Yeah, that's a good question. So if we want to get our thermodynamic product, that is favored typically under high temperature conditions. All right? Now the question is, what about this one? Is it necessarily going to be our kinetic product? Well, we got to think about it, right? Kinetics is in reference to speed, meaning how quickly it can occur. All right, so what I want to do is I want to go back and look at this reaction, right? So imagine you're the HBr, and you've given up your proton to this specific carbon atom. That means that the bromine is going to be pretty close to this carbocation right here, right? So in space, it's going to have a close proximity to the spot that it needs to attack. If we look at the molecule on the right, though, once we deliver this hydrogen on the far right, that bromide ion has to find its way a few carbons over before it can attack that carbon. So it actually has to float through space before it can find the thing it's going to attack. Which one do you think is going to occur faster? The one on the left, simply because it's closer to the site that it's going to attack. So that's going to be our kinetic product. Yep.
Does that also mean that between our enantiomers, one favored slightly more than the other as well?
Not necessarily. So you were asking about one enantiomer over the other. That hydrogen wasn't exclusively installed to one face over the other, so we can't say that with any certainty. Yeah. All right, so this is going to be our kinetic product. That's, we'll try to take a look at a few examples. I'd have to see that in the context of an example. Yeah.
So if something's called thermodynamic and kinetic, are you going to get very much other?
So you're stealing my thunder. We'll come back and talk about that. All right. So the kinetic product is simply due to the Br minus doesn't have to float as far to find a positive charge. And I'm going to use the scientific term float. So this reaction is faster. Or I should say, has a lower activation energy. We'll try to use the appropriate scientific terminology. All right. So let's take a look at this with a reaction coordinate diagram. We haven't really done that since first term. All right, so we've got energy over here. We've got reaction progress over here. And we know that our thermodynamic product is going to be lower in energy than our... In fact, I'm just going to draw it out. Is going to be lower in energy than our kinetic product because it's the result of a more substituted alkene. Does that make sense so far? Our starting material was going to be the same regardless of what product we're making. And then the kinetic product, we said, has a lower activation energy because it doesn't have to float as far to find that positive carbon. So we'll draw it like that. Where the 1,4 addition product, it actually has to move a couple positions over to find that positive charge. So it looked like this. So what I mean by that is the kinetic product has the lower activation energy. Versus our thermodynamic product. If we think about our thermodynamic product, it's got the largest drop in energy. Has a larger delta H or delta G, depending on what you're looking at for this given reaction. Delta S isn't really changing much for either of these, so oftentimes you'll see it written as delta H rather than delta G. Make sense? All right, so let's do an example and let's practice. Let me change this a little bit, sorry. I'm going to test your ability to draw polygons. All right, let's try this one. I got you all used to drawing these. 6-membered rings. Now I threw an extra carbon in. So I'm going to just draw my 7-membered rings because that might take me a while. So let's go through and find our intermediate. So we know in the first step, one of these alkenes, doesn't really matter which one, is going to attack HBr. Why doesn't it matter which side does the attacking? It's symmetric. If it's not symmetric, then you need to account for both possible products. All right, so in this reaction, we want to form the more stable carbocation. So the question I have for you is this double bond goes there. Where do we want the positive charge to be? Do we want the positive charge to be where that red position is or the blue position? Red position. Why? The blue position's tertiary. Resonance. I forgot to wear my resonance shirt today. Dang it. All right. So we got the positive charge here. We know that resonance is more important than substitution. So we can delocalize our positive charge and put the positive charge here. I'm just, for now, going to draw in the hydrogen. We know in step 1, our hydrogen must have been installed right there, right? All right, so now if we think about bromine attacking back in, or bromide, I should say, it can attack either one of these positions. And for the time being, let's just neglect stereochemistry because there's going to be a lot of different stereoisomers that could result. That's a terrible roof. All right, so we've got 2 different products. All right, which one is going to be our 1,2 addition product? Left or right? Left. If we think about it, right, we added in 2 things. They're 2 carbons away, so this would be 1,2 addition. This would be 1,4 addition. Because they are 4 carbons away from one another. All right, which one's our thermodynamic product? The left or the right? Why the left one? More substituted. All right. Because it has a more substituted alkene, it must be our thermodynamic product. All right, let's think about kinetics. Which one can be formed easier, meaning faster or with the lower activation energy? The one on the left? Why? Because the bromine doesn't have to float as far, right? So this one is the kinetic product too. All right, then we start to ask ourselves, well, is there any possible way to favor the 1,4 addition product in this example? Can we change the temperature? No, because if we cool it down, we're going to favor our kinetic product, which is the exact same product. If we heat it up, we're going to favor our thermodynamic product, which is the exact same product. So in this specific situation, this is absolutely going to be our product. This one is very unlikely to form on the left. So students get confused with this a lot. Oftentimes students get stuck in this like memorization mode where they always want to say 1,2 addition products are kinetic products, 1,4 addition products are thermodynamic products. Not always. You have to break it down and ask yourself these questions. More substituted alkene is going to be your thermodynamic product. 1,2 addition, on the other hand, is always going to be your kinetic product. So let's make a note. The kinetic product is always going to be 1,2 addition. And that's due to the nucleophile being in close proximity to that carbon that it's going to attack into. And then your thermodynamic product is going to be your more stable alkene. It's not necessarily going to be your 1,4 addition product. And then like we saw here, sometimes your kinetic and thermodynamic products are going to be the same. All right, so let's say we want to favor our thermodynamic product. We mentioned this previously. Would that be favored under high temperature or low temperature conditions? High temperature, right? So we could say favored, at high T. All right, kinetic products, on the other hand, we don't need very much energy to get over the activation energy barrier. In fact, we don't necessarily want too much energy because then we might go over the barrier to get to our thermodynamic product. So it's going to be favored at low temp. So it does give you some control over which of these will be favored, meaning which one will be your major versus minor product. Yep.
So then if your product is both of them, you just crank it up.
Yeah, so if your product falls into this category, you might as well just blast a lot of heat into the system, right? Because it doesn't really change the dynamics of anything at all. In fact, oftentimes when you do the low temperature reactions, what you do is you get dry ice. You can even go to Fred Meyer and get dry ice, and then you get some acetone. You dump the acetone over the dry ice, and it starts forming this like bubbling Halloween mixture, and that goes down to negative 78 degrees Celsius. So you can really run these reactions quite cold. There's a whole bunch of different techniques for getting these temperatures down very, very, very low. The big thing is you have to have enough energy to overcome your activation energy without so much energy that you compete and get the other product. So that's where I'm going to leave it today. In general, though, on exams, I'm not looking for specific temperatures. I'm looking for hot or cold. So you can just write hot or cold, and that's fine with me.